Welcome to this video. In this video, I will be taking you through the steps of the Deutsch-Jozsa algorithm. And in some sense, the steps are very simple. Once you know what is the oracle doing, what is this box doing, and what is the Hadamard gates doing on a n qubit basis state. So these two things I have talked about in the previous video. I said how this oracle OF gives a phase kickback, and we will use that. So phase kickback. And I also discussed how this Hadamard gates, how they act on basis vectors of n qubit state. So to remind ourselves, the Deutsch-Jozsa problem is a promise problem, and it works under the query model of computation. So the problem is that we are given a promise that a function is constant or balanced, and we can query the function, and the question is we have to determine what is the function. Is it constant or is it balanced? Now as I talked about in the previous video, classically you need either two queries in the best possible scenario, or you need basically 2 power n divided by 2 plus 1 queries in the worst possible scenario. But quantum mechanically we only need a single query. And what is the single query? The single query is we put a string of zeros, a bunch of zeros, and then we proceed through this circuit, and we will at the end measure the state in the zero eigenstate. So basically in the end we are measuring it using this state only. And in the computational basis, so this is equivalent to 0 tensor n. Basically this is the state. And so let's go through the steps slowly. The first step is what happens after the first Hadamard gate. So after the first Hadamard gate, we have 0 acting with Hadamard gate, and we get a state like this. So this is ignoring this factor, it is an equal superposition state. So it is an equal superposition state of all the bit strings that are possible of length n. So this is the first thing. And how does this come about? It come about by the action of Hadamard gate that we discussed in the previous video. So after this we are going to proceed to the second step, which uses the phase kickback. So now this also we know that for each bit string, this oracle OF, it gives us a phase kickback of minus 1 power f of x. So this was also talked in detail in the previous video. And this means the second state is of this particular fashion here. So you can see that you are getting phases due to this oracle. And now the third is again an application of Hadamard gate. So this application I have written in here. So this is the third step after application of the Hadamard gate. So what is this state? It is easy to see. We have to just act with Hadamard gate on this particular basis state, and this introduces a factor of this the 2 power n by 2 which contains how many qubits we have, and then it has the factor that is introduced due to the action of Hadamard gate with this binary dot product that I discussed in the previous video. So with this we have almost understood the output state of the algorithm, which is of the form of summation over k ck times k. So I am taking this as k, and ck is this particular state here, this particular coefficient here, sorry. So this is a coefficient, and now we know that we have to measure it on 0. So what is the probability of getting 0 state? The probability is obtained by simply putting k equal to 0 bit string. So k is the 0 bit string n times, and then you have this term as dropping out. This term will drop out, and then you take the mod square. So then what you have is something that I have written here. So this is the output, 1 over 2 power n summation over all bit string, this is summation over all bit string, minus 1 power f of x. Now the idea is this value will be 1. So you have now measured your state, and now you will get a value, and this value will be 1 if f of x is constant. This is because if f of x is constant, then all of these coefficients, it will just simply add up over all the possible bit strings, and that will give you 1 because there is a prefactor of number of bit strings in the front. And if f of x is balanced, these plus and minus, they will cancel out because you will have equal number of zeros and equal number of minus 1. So you will have equal number of plus ones and equal number of minus ones appearing. So this means we can just measure and then check if we are getting 0 or 1. If the output is 0, we say it is balanced. If it is 1, we say it is constant. So, and we are done with the problem. Now there is a small variation of this problem which is called Bernstein-Vazirani problem, and in this it is a different kind of problem which says that the promise is not that f is constant or balanced, it is that there exists a bit string s such that f of x is this. So this is just again binary dot product, and we know that the function takes this particular form, and the question is to determine the string that defines f, for example. So this is the question, what is s? So this is the question, and this is again just Deutsch-Jozsa algorithm but without the measurement part. This is very simple to see. So the idea is, if I ignore the measurement here, if I just ignore this measurement, then I will come up till this 3 step. So the step 3 gives us a state of this form, which is a ck k sum over k, and the coefficients I have shown here. So these ck's are the coefficient, and I write the coefficient here. Now I use the fact that the promise is, the function is s dot k, s dot x. So f of x is s dot x. Then this means I have s, an XOR operation, then k dotted with x. So this is like a distributive law of multiplication over addition, just in the case of binary. And this is 1. This is 1 if s plus k is 0, because if this is 0, this factor goes out, and the sum over all the binary, sum of all the bit strings of length n is 2 power n, so you will get 1. And what this means is that you will exactly have s XOR k as 0. So s XOR k as 0 implies s equal to k, because you can add XOR k on both sides. And this means that your final state has only one coefficient which is equal to the bit string. So your final state has already the form that the state itself is a basis vector, and that basis vector has the value of the bit string. And if this is not the case, it will always be 0. This is because there will be equal number of plus ones and minus ones appearing. So with this, I come to the end of this video. It was a short video and was a follow-up of the previous video. In the next video, I will talk about the Grover's algorithm. So particularly the Grover's algorithm is related to the problem of searching an unsorted database. And the idea is, if I just discuss, it is that given a function f, you have a promise that only when the bit string is equal to w, a specific bit string, the function is 1 and it is 0 otherwise. And the question is, how can we find w? So w is something that kind of marks the function, or it is kind of a marked entry. It is an anomaly, and we have to find it in the set of 2 power n bit strings. So with this I end my video. Thank you.